Right, morning lads. Hope you're well. Today we're going to spend a bit of time looking at graphs and how graphs can give us a lot of information about different materials. In the notes you've taken so far and in the content we've covered so far, you should have come across, or we will have come across, force extension graphs. With these graphs, you will remember from your GCSE a required practical where you had, say, a spring. You may have done this with an elastic band as well. And what you do is you have a spring with weights attached, and then you add weights, you measure the extension, and then what you do is you plot a graph of force, and you get the force from how much weight has been added to the spring, and you plot it against the extension. So one of the GCSE required practicals. We're going to look at that a bit further today. The first thing I'd like you to do is pause the video and sketch these graphs that I've drawn for two different materials, A and B. I'd like you to, as well as that, label the key points on the graph, and I would also like you to think about what words you could use to describe materials A and B. Now, to plot a force extension graph, this doesn't need to necessarily be a spring, like what you did at GCSE. It could be a length of wire, it could be an elastic band, it could be any material, because last lesson we saw that any material made up of atoms bonded together can be modelled as a collection of springs in parallel and series, so can be modelled as a spring. So to get this, pause the video now, get a sketch of that graph, label the key points, and have a think about how you could describe the differences between materials A and B. Okay, so I'm now going to add some annotations to this graph. I would like you to add these annotations for me to your notes as well, because these are some of the key ideas you need to know. So if I look at both these graphs, I can label this first point of interest about there on that graph. Now, that's an important point on the graph. Up to that point for both of these materials, the force and the extension are directly proportional. So we can say for that section of the graph, that material is obeying Hooke's law. This, on both of these graphs, is called the elastic limit. After this limit, so it's the elastic limit there as well, after this point, the force and the extension are not directly proportional. And we can actually give a name to the whole region of the graph up to that point. So if I just highlight it, you can do this in whatever way you want. If I highlight that part of the graph and that part of the graph there, during that point, what we've got is a period of elastic deformation. Now, what does elastic deformation mean? Well, it means that if you've extended it, it will return back to its original length. So I've got a spring here. If I extend this spring, it extends elastically, and therefore, when I let go and remove that force, it removes back to its original length. Now, if I was to extend this spring too much, and you may have seen this with your required practical from GCSE, it will go past the point where it will return back to its original length. So it's elastic deformation so long as the force is directly proportional to the extension, and when I remove that force, it goes back to its original length. Now, if we look at the next part of the graph, so during elastic deformation, you're at a point where the force is directly proportional to the extension, i.e. it obeys Hooke's law. Now after that point, there's a change in its behaviour. The force is no longer proportional to the extension. So we have this period here and that period for that graph there. This period is the opposite. Well, it's not the opposite, it's a different type of deformation, and we would call that plastic deformation. Now once you're in the stage of plastic deformation, you're at the point where it's not going to return to its original length. An obvious example of this is just a piece of plastic, and if I stretch that piece of plastic, it will never return to its original length. So there might be a really small period. I could apply a very small force and it could go back to its original shape. But anything above that small force will result in a material that's permanently deformed. And that's called plastic deformation. So depending on the material, depending on what you're applying the force to, you have different periods of elastic deformation and then different periods of plastic deformation. The important point here is beyond that elastic limit, that key point on the graph, that material does not obey Hooke's law. What I'd like you to do now for me is just pause the video very briefly and have a think about, I've given two materials here, A and B. I'd like you to think about what the differences are between those two materials. So the first question we could ask ourselves is, which material is stiffer? So as you've come to it before, the gradient of this graph gives you the stiffness. So we've got the fact here that A has got a steeper gradient, so this is going to have a greater stiffness, and by that you know, because the gradient of this graph gives you the spring constant, you're at a point where you know that this material A is going to have a larger spring constant than this material B. The one other thing, and we're going to go into more material properties in a minute, is this material has got a larger period of elastic deformation compared to this. Now when we go on to look at Young's modulus graphs, we'll be able to characterise this in a bit more detail. But if you've got a material that doesn't do a lot of this plastic deformation, what we'd actually say is it's more brittle. Whereas B, if it has a larger period of plastic deformation, it would be called ductile. So if we look at A, we'd say this is a brittle material or more brittle than B, and this would be ductile. We've got the fact here that the gradient gives us K, the spring constant or stiffness. The other thing that's relevant about this graph is the area underneath it. Now, remember how this graph is being produced. We're adding force to these materials and we're extending them. Now, if we go back to our energy, work and power section, we know that when we move a force through a distance, we do work. And when we do work, we cause an energy change. So I could ask you, when we extend these springs, what is the energy change going on? Well, we're applying a force through a distance, so we're doing work. And the energy change here is an increase in elastic potential energy. Now, if you do maths, if you do further maths, you'll be familiar with the idea of integration from first principles. But you can see really that if we say work out the area under either of these graphs up to a point. So say I pick that point there and I work out the area under that point. From that point. What I'm having to do effectively at each stage, and if you were to work out the area of this graph exactly, and you would never do this, but you'd have to divide it into small pillars, small rectangles, and you'd have to work out the area of each rectangle and then add them together. That's what integration does for you. With this, to work out the area of each of these rectangles, we'd be doing a force times by an extension at each point. What's the relevance of that? Well, remember from our energy, work and power unit, we saw that when we do work done, it's equal to a force times by a distance moved. So if we're working out this force times distance moved for each section, effectively the area under this graph, the area under the force extension, extension graph, is equal to the work done in extending the material. And with that in mind, with the area under the force extension graph being the work done in extending the material, that's got to be equal to the elastic potential energy stored by that material. So I do need you to know for this graph the important points that the gradient will give us our spring constant, and the area under it, up to whichever point that you want to go to, will give us the elastic potential energy stored. Now, with that in mind, what I can do is I can derive a formula for the elastic potential energy stored. So if we do that, then we can see that up to the point where that material obeys Hooke's law, the area under the graph up to a general point where the force on it is F, the area under that is just going to be the area of a triangle, a right angled triangle. So we know the area is the energy stored, so we know we're going to be dealing with a half base times height business. With this, you're going to see that, well, the base of the triangle here is our extension, delta L. So it's going to be equal to half times by delta L times by the height. Well, the height is given to us here by the force. And there you've got the formula for your energy stored. That is given to you on the formula sheet. So for elastic potential energy, you've got equals a half F delta L, as it's usually written. Now, a really handy tip here is to recognise that this force can be given by Hooke's law. We go back to that F equals K delta L. And if I substitute that for force into that equation, I can have a half K delta L times by delta L. And that simplifies nicely down to a half K delta L squared. Really key here. This formula is not given on your formula sheet. But if you're looking for a quick way of working out the energy stored in a spring or material, and you're more likely to know the spring constant of that material and the extension rather than the force applied. I know they're very closely related, but if you're looking to work it out quickly, this is a far easier formula to use than having to work out the force and then substitute it into there. So please just bear in mind that we've got this formula, which comes from working out the area under a force extension graph, and we can then get this half k delta L squared, which gives us the energy stored. And it's telling us that the energy stored is proportional to the square of the extension. So in our last lesson, we looked at Young's modulus, and we said that the reason why we introduced Young's modulus is so that we've got a measure of the stiffness of a material which doesn't depend on the amount of that material you've got. And we've said that that could be very useful for engineers who want to decide what material they want to use for different applications. Today we're going to take that a little bit further. We said Young's modulus tells us about the stiffness of the material. From the graph we've just looked at, this force extension graph, there's a lot more interesting about a material than just how much force you need to give a particular extension. And what we're going to do is we're going to look at another type of graph for different materials. A lot of what I say, in fact most of what I say, that applies to the graph we're going to look at now, like what's called a Young's modulus graph, can be said for these force extension graphs too. Yet again, the reason why we like to use Young's modulus and why it's often a more useful quantity in engineering is because it doesn't depend on the amount of the material. But what we're going to see here is by looking at the Young's modulus graph, it will tell us a lot about how the material behaves. And how the material behaves in general is often more useful to know, or is useful to know in addition to just how much force it needs to give a particular extension. Now, Young's modulus graphs are always plotted in a standard way. On the y-axis, we always plot the stress. Now, remember, stress is your force per unit area of a material. And on the x-axis, we plot strain. The change in length divided by the original length. In other words, the fractional extension of the material. With these graphs, they're quite easy to plot for different materials and to get the data. In a similar way to what you did for GCSE when you looked at the extension of a spring versus the force applied, you can do that for different materials. Now, when we're back in school, hopefully we'll be able to do this year and be able to work out our own graphs for different materials and learn how to plot them. And there's a few subtleties that we'll cover then, but the main thing is you apply a force to these different materials, whether it's steel, copper, brass, and then you measure the extension. Now, the difference between that and the practical that you will have done at GCSE is the extension of a spring is quite easy to measure. You can use a meter stick and you can use a marker on that spring. What's more challenging when you come to materials like a steel cable, for example, is the extension becomes very small. So we need more accurate equipment for measuring the extension, but we'll look at that at a later time. The point is, for any material, you can plot the force against extension. You can you can get the force and extension. And from that, you can work out the stress. You do the force for every point, and you divide that by the cross-sectional area. And you can work out the strain by just dividing the extension by the original length. So what I'm trying to say here is that if you've got a graph of force and extension for the original material, all you need is the cross-sectional area and the original length, and you can get one of these stress-strain graphs. Now, I'm just going to draw a general stress-strain graph, and your work for the rest of this lesson is going to be looking at stress-strain graphs for different materials and seeing what you can deduce about them. So, in the same way, it makes sense to draw something that goes like this, and then like that. Yet again, this will look different from different materials, but the points that I'm going to label here apply to any material that you do this for. So, just as we did before with the force extension graph, same thing applies. We've got this section here, which I'm highlighting in green. This is the period of elastic deformation. And up to this point here, this material is obeying Hooke's law. Force is directly proportional to the extension. And then after this period, you've got this section here. So we've had the elastic deformation, and this is going to give us the plastic deformation. Remembering that the plastic deformation is when the material is no longer going to return to its original length. It's going to be permanently deformed. In a later lesson, we're going to see how that can be shown on the graph too. And it gets to this point here. Now, we already know what the name for this point on the graph is. This is going to be our elastic limit, beyond which you get plastic deformation. And up here, the peak of this graph has got a very important name. Now, we can see at this peak, this material is under its maximum force. And this is the most force this material can generally hold without breaking. Now, this is given a name, and it's given the name the ultimate tensile stress, beyond which beyond which the material is effectively going to break. So that ultimate tensile stress is an important quantity for different materials that you're using. This next section of the graph, after this point of ultimate tensile stress, is quite an interesting one. And this gets us to here, the end of this graph. This is the breaking point of the material. So that's the point at which the material breaks. With this, and what's slightly strange if you think about it, is that you're adding, or you're not adding as much force, but you're still getting an extension. In fact, the force the material is holding is actually going down, but your extension is still going up. And this can actually be for quite a large proportion of the graph. What's happening here is the material, and probably be best to show you this in terms of a diagram. So if you're applying a force to a length of wire, this is your cable, and you're applying the force to it using some masses, what would be happening here is that material will be extending, but you won't be adding any extra force. In that case, if we were to zoom into that material, if it was just a wire, it would start off looking like this. It'd be a uniform sort of cylindrical wire. Now, as you get to that point, what starts happening is, and this is before the breaking point, is this wire actually starts getting narrower. So up to its breaking point, it goes from being this sort of uniform cylindrical shape to a shape where it's actually beginning to narrow a bit. And what happens is that narrowing increases until the material breaks. That's what's happening in that region of the graph. I've never seen this tested in the exam, but this process is creatively called necking. So this is going to be the necking region of the graph. Yet again, for some reason, never seen it tested in the exam, but that's what's happening during that process, and that's why, without adding any extra force, we're getting a larger extension, because that wire is getting weaker. Few important things to point out here. If we want to find the Young's modulus of a material, remember the formula I gave you for Young's modulus last lesson. Young's modulus is equal to stress divided by strain. So if I were to work out the gradient of this graph, now what's important here is, for the Young's modulus, we're only interested in the gradient during the point where this graph is proportional. The stress is proportional to the strain. Now, in this case, if we were to work out the gradient, we would be doing stress divided by strain. So that's why for that graph, if we've got an important note here, the gradient of stress strain graph is equal to the Young's modulus of material. Really importantly, it's only the gradient up to the elastic limit, and that's important to the definition. The other important thing about this graph, and I'm not going to derive this here, but it is relatively straightforward to show, is what is the significance of the area? In a similar way to our force extension graph, the area is to do with the energy stored, but specifically the area under graph, in this case, is equal to the energy stored, again this is elastic potential, per unit volume of material. Interesting how the gradient gives you this Young's modulus, which I said is a measure of the stiffness of the material, not depending on the amount of material you've got, and the area under gives you a measure of the energy stored by the material, which doesn't depend on the amount of material that you've got. So this fact here I've not seen I've not seen tested. That doesn't mean that it couldn't come up. So it is worth knowing. Importantly, comparisons between these graphs tell us how different materials behave. So I could plot another material on here. So let me just, for sake of argument, do one like this. Now that's quite a good comparison. How can you compare those materials? Well, if I was to say this material is A and this material is B, how can we say those materials are different? This is going to be stronger. We can apply more force to this material without the material breaking. So in other words, it's got a higher ultimate tensile stress. What is important here, and this does get tested quite a bit in the exam, is this material, for most of its length, is elastic deformation. So very quickly, near the ultimate tensile stress of that material, it'll be pulled and then it will very quickly break without this long period of plastic deformation that you get with that material. How would you describe or characterize the difference between both of those? We'd say that this material A is ductile. Ductile means easily drawn into wires, and it does have a period of elastic deformation. So just as a note here, and I'm going to stop you now and let you do a little bit of independent work on this. It's worth knowing here, it's an important point, that if a material has large amounts of plastic deformation, as a general rule, we would say that means that it's ductile. Here on the graph, we've got the opposite of that. A material which is going under elastic deformation almost entirely, with a very small period before it breaks of plastic deformation, if at all. The opposite of being ductile is brittle. So think of a biscuit, easy to snap. You've got here a large amount of elastic deformation and a very small amount of plastic deformation. And that would mean it's brittle. Just an interesting point here to note that if I was applying force to material B, there'd be nothing that would be happening to show that I was applying a force. You'd be applying a force and it'd be very hard to notice any extension of that material. However, for A, you'd be able to notice that material extending. Please bear this in mind. For the work I'm going to set, you'll come across lots of other key words that you do need to know. Out of all these key words, the difference between ductile and brittle is one of the most important. The other thing I'd just like to say, if we kind of bring this into, well, what we've talked about A and B, what could materials A and B be? A brittle material, a good example of a brittle material, is something like cast iron. So we could think of material B being brittle as, For example, something like cast iron. One of the reasons why, for example, we can't make a bike out of cast iron is because it would go over a bump and it would almost certainly crack. A ductile material, the best example of a ductile metal would be something like copper. And that's why copper is one of the reasons, other than it being a good conductor, that it's used to make electricity cables, is because it's easily drawn into wires. Another example, steel is less brittle than cast iron. By adding carbon to cast iron, you can get steel, and that generally provides a more useful material because it doesn't have this very small period of plastic deformation. In general, ductile materials are more useful in engineering than brittle materials, and that's why steel, or the development of steel, actually had such a large impact on the development of society, because it can be so much more useful than cast iron in terms of making stuff. So I'll set the rest of the task on Microsoft Teams, and we'll look at some questions around this.